Hi guys, my name is Sarah Jane Protz and I am a research engineer working at Specific in Swansea University. So if anyone wants to ask any questions throughout on anything particular who is live, you are more than welcome to. There will be some interactive bits in this as well where I will ask questions. You're also more than welcome to talk then. But in the meantime, if you guys would like to meet yourselves or just listen, that would be fantastic. But my work specializes mainly in solar cell design. And today we're going to be talking about how it's created. So this is on printed electronics for off-grid homes. But when people think about printing, traditionally what they think about are graphics, so pretty colors and the things that come out of your inkjet printer at home. So when it comes down to colors, typically it can be split up into four, which are cyan, magenta, yellow, and black. And when they overlay, your eye tricks you into thinking they make up a series of colors when it's actually only a few. So that has been used for centuries to create things like textiles, wallpaper, and now still being used for a variety of applications. But that's not what gets me excited. What gets me excited is taking these capabilities to mass manufacture things at a very high rate onto flexible substrates and enabling it to have more complex properties. So this is made possible because an ink is made up of four main components. So this is the resin, which will combine with your solvent, whether it be an alcohol-based, water-based, whatever it is. And then if you have a few additives together and you mix this with either your pigments or your other materials, you create an ink. And if you want a functional ink, you can add things such as conductive materials like silver, copper, carbon, or if you want it to change colors, you can add other things. This enables us to create a wide range of functional materials. And these come in a very wide range of viscosity. So when I refer to viscosity, I'm talking about the thickness of the fluid, so how hard it is to shear. But it means that we can create them in a very wide range. So functional materials. So not only is there conductive, which I mentioned earlier, we've also got things like photochromics, which change color and light, thermochromics, which change color and heat, phosphorescence to glow in the dark, hydrochromic, which you might want on some waterproof clothing or on a waterproof screen in your car, biomarkers, which are essential for biosensors, especially ones like diabetes tests, which are actually printed, and many other things. So this is where you guys who are listening live can get involved. We have a series of different images on the screen. So can anybody tell me which of these can be printed? So if you have the ability to unmute yourself, please do, and just quickly shout out what can be printed out of this lot.
Printed circuit boards.
Yes, those can be printed. What else?
Custom prosthetics.
Yes, perfect. Those are most certainly printed. Anyone else want to hazard a guess? One more. Anyone? No, that's more than fine. Okay. So straight off the top, these four things can be printed exactly how they are. So glucose monitoring biosensors, those are actually screen printed, which we'll go over later. So flexible mobile phones, these are made of OLEDs. These are most certainly printed. Custom prosthetics, those can be printed using 3D printing techniques. And also curved televisions, those are also OLED. However, it was a trick question. All of them can be printed. So in the case of batteries, those can also be screen printed to make them flexible, thin, and easier to use. Those are currently being developed. Antennas can also be printed, such as radio frequency ID tags, which if you have some clothing from places like Decathlon, if you have a look at your tag, you will be able to see that they have that embedded in them. And therefore, they can be printed. Heaters, this one might have been given away earlier when I was chatting to you guys. Those can also be printed, and I will show you a demonstration of one later. And pressure sensors, those can also be printed. So all of these things have the ability to be printed, mass manufactured, and made thin and flexible where needed. However, all of these things can't be done on a single press, so there are a variety of printing presses available. These include flexography, which for anyone who's used stamps or done potato printing when they were younger, it's basically that principle. So the ink transfers from the feed to this analog roll, which is a roll with lots of tiny little holes in it, which have been engraved. These transfer to a 3D plate, which is like a stamp except on a roller, which will then transfer the ink onto the substrate and on. Another one is aerosol. So some of you guys may have used aerosol cans to do spray painting. This is a far more complex version of that, which can be used to print very fine, very conductive features. Inkjet. So obviously a lot of you will know inkjet. That is something you may have currently sitting in your house and printing off your homework, but it is also used in mass manufacture of a variety of things, including magazines. Gravure. So gravure is one of the more expensive of the presses. So this one, like your analog roll here, is covered in lots of tiny little holes, but these perfectly represent the image which is being printed and enable them to transfer directly onto the substrate. So these are used in things like glossy magazines, which provide a really nice high quality image. So if you have things like National Geographic, that's probably done using gravure. Then you have offset lithography, which uses a combination of water and ink, with the water repelling the ink to enable a pattern to be deposited. But the one we're going to discuss more today is my personal favorite, because I spent 4 years of my life slaving over understanding this. Although it's actually quite simple, it's also very complex in terms of interactions, and that is screen printing, which we'll be looking at a little bit more today. So what is screen printing? Screen printing is a flexible process used for a wide variety of industries. It is actually used to produce the majority of printed electronics today, over 90%, as it produces most of the glucose biosensors, other biosensors, things like heaters, and it's also being used in solar cells, as we'll go over later. It is an industrial high-tech process. It's been used a lot in the graphics, and now it's being used to print electronics as well. And in some cases, it is the only process available to print some of these inks, as inks containing very large particles, such as big chunks of carbon. They are very viscous because they have the big particles interacting with each other. They're actually really hard to stir, and they are very, very, very viscous. And this means that it requires a press which is capable of printing something that thick, and screen printing is the answer. So how does this work? So you have a little diagram here. And if I stop sharing for a sec, I can give you a basic demonstration before I show you the other clips. So here is my screen. I will explain in a little bit what it is made up of. And if I tilt the camera down, you'll be able to see that if we were to have a substrate, such as one of my coasters, go in the middle, we're able to then levitate our screen above, not levitate, but prop it above at a set gap. And then you will have a squeegee, which I'll describe a bit more in a sec, which will force your ink, which you can place here, down and onto your substrate as you force it down and go across. But more on that later. So if we go back to our presentation. Sorry about this, guys. A few technical difficulties. And there we go. So sharing the screen again. So what I'm about to show you is some printing I did a few weeks back. So what I'm doing here is printing a carbon pattern, which is used in perovskite solar cells, which I'll talk a little bit more about later. So as I briefly described then, what you have is the ink getting placed onto the screen, evenly distributed across with a blade known as a flow coater, and then the polyurethane squeegee, which I have here in my hand, is being used there to force the screen to come into contact with the substrate and enable the ink to pass through in the exact pattern that you want it to be in. So the issue with screen printing, which I found out, is that it has a lot of parameters. So you have your squeegee, which can come in a variety of types, hardnesses. You have your screens, all of which have different hole sizes. So the size of the hole will determine how much ink flows through, the thickness of the ink that can flow through, and the pattern type. All of these things can change. The ink type, it can be a variety of viscosity, so a variety of thicknesses. So some of them will be very thin and run like water, whereas others will be thick and a bit like a really, really thick honey. So it can be just about anything. This gap between the substrate and your screen, that will also change. All of these things are a pain in the butt, but you don't have to worry about that. That's my job. So going over the screen. So the screen I just showed you is made up of a stencil, which is on top of a polyester woven mesh or stainless steel, but I can't afford one of those, so I'm just showing you the polyester one today. It is very finely woven, a bit like a blanket. And then to determine what can and cannot pass through this mesh, you have an emulsion-based stencil on top, which is then cured, dried, and then the wet rest washed off as shown in the diagram here. And altogether, this enables us to only deposit the exact pattern we want. But some of you may think, how is this different from me getting a laser cut stencil and just coating it on? The reason being is you try doing some letters, preferably like an O, which are unconnected. It's very hard. This enables you to have far more control. It enables you to do complex patterns, and the woven mesh means it all stays in contact together, and you get the exact thickness of the ink deposited you want. So there's a lot of things you can change to control exactly how it goes down, which makes it a really cool process, in my opinion. And the other thing, my favorite thing actually, is the squeegee. So what I have here are two squeegees in my hand, which are demonstrated on the screen as well. These are blade squeegees, as demonstrated. They're also diamond-shaped squeegees, which go only at 45 degrees to the mesh. So there are a lot of different things we can do with these squeegees. They come in different hardnesses, which means that they will flex differently, allowing different amounts of ink in. And the harder the squeegee, so this one's quite rigid, I'm holding in my hand right now. A harder squeegee will have more interaction between the substrate and the mesh, and this means typically less ink is deposited, which enables us to get really nice, crisp, fine features. But if we want a nice thick deposit, you can go for something a little bit more flexible, like this one currently being played with in my hand. And this means that when it flexes, it will allow more ink to pass through. So there are lots of designs to choose from, all of which have an impact on the quality of your print, and all chosen according to what you want to make. But rather than going deep into the science of screen printing, which if you want to know more about, please let me know at the end. I can talk to you for hours about it, but rather than bore the majority of you, I'll give you a few examples of what can be made. So a big one at the moment is active and intelligent packaging. So these use things like thermochromic paints to tell us how cold something is. So if you want a nice cold drink, which might be quite nice in the garden right now, it will change color at a certain temperature to tell you if it's cool enough. You can also get hydrochromic paints to indicate humidity, which is quite good if you want to check the freshness of some foods. And you also have electroluminescence displays, which make really pretty fancy light shows for your packaging. So all of these things are actually really useful. And as you can see with the thermochromic chips on here, you're actually able to tell how cold the packaging is. You can also have extra things printed to tell you how long it's fresh for. So you're not just going on the sell-by date, but you also have a bit more feedback to know, is this thing going to give me food poisoning? Yes or no. And so it's actually really useful. But the prettiest stuff are electroluminescent. Sadly, I don't have any to hand right now, which is probably best as it requires a very high voltage, which I don't want to play with live. But this enables us to have really nice, eye-catchy, flexible, very bright luminescent displays. So you may recognize some of these from watches. So these are using old watches, some old car displays, but also have a lot of uses today. These are also screen printed. But what you're here to learn about. So my current work looks at producing printed electronics for off-grid homes. I work for Specific, whose main goal is to produce buildings as power stations. So the house you see in front of you here, this actually exists in Bridgend right now as a part of a new social housing scheme. Hopefully they will have someone living in very soon. These have flexible solar power panels on the roof. They have a big battery out in the back garden and have a lot of other cool tech going into them. So at Specific, we do research into things to enable this. So my main work looks at producing perovskite-based solar cells and resistive heaters, which can be used as a new form of underfloor heating. So if we go a little bit more into detail, so what are perovskite solar cells, for those of you who don't know? So perovskite is a relatively new version of solar cells, which are better efficiency in our delightful British weather. Yes, we're not sarcastic, but it's more efficient in lower light levels. It's not perfectly stable yet, but my job is to try and scale them up and get them into manufacture, and they can be really useful to us as we are all looking to try and decarbonize at the moment. So how are these things made? So three of the layers and an extra layer if you want it thicker are screen printed. These include your titania layer, your zirconia layer, and my favorite one, the carbon layer on top. And all of these things together enable us to produce a very thin and potentially flexible, if you print it onto the right stuff, solar cell, with research being done into how to make them transparent as well. So really great stuff. But my favorite run, which I can demonstrate to you in a bit, are resistive heaters. So these can be fully screen printed and are actually rather straightforward to create. So in this you have a carbon and silver layer, and these could be used in floor tiles, in clothing, in automotive parts. So if you want a nice warm back, then you can get them printed on the back of your seats. And unlike typical cabling, which you might have for heating, these can be used to produce different areas. So you can have the pattern designed so it heats up exactly where you want it, and you have the full area heating you rather than just a single line of wire. And they have a lot more applications. But today I'm going to tell you, if you wanted to do this yourself, how you would make your own heat up coaster. And I'm going to take you through the entire process that I do to make these things. So this will start with how inks are made. You can also buy inks, but I'll explain to you how they are made from scratch. How you screen print the carbon layer, and then how you do the silver layer, go for each step, then how you connect this to a power supply, and then hopefully we'll be generating heat, and I'll be showing you that live as my little demo. So first things first, how do we make the ink? So what you need to do is you need to take your polymer granules, so your resin, and combine that with your solvent, whether it's water or alcohol based. And what I usually do is put it in a big flask, combine them all together, put them on a nice hot plate. So this particular one needs to be heated to 70 degrees. Then we have a big overhead stirrer with a blade at the bottom going round and round and round for around an hour until it was all nicely dissolved into the solvent, creating a nice resin base. After that, to make our ink, we can then add our functional materials or our color granules or whatever it is you want as your main particle. So in this case, it would either be silver or carbon, but normally in the case of the ones I get, they are usually agglomerating, so all sticking together, which would make a really horrible clumpy ink, and that's not very good when you want a good performance. So these would then be milled. In this case, it would go through a triple roll mill to make these particles get finer and finer and more evenly distributed in the ink. So you can see one of my examples here of my rather grainy carbon ink going through then coming through these rollers and coming out at the end. Admittedly, it doesn't look that great coming out, which is why it then needs a final stir to improve its consistency, and voila, you have ink. So how do we do it next? So the next thing we do is we slap that ink onto our screen, and then we print it with whatever settings we need and whatever pattern we need, and that would then go through the dryer. And this is what my coasters look like after only the carbon layer was printed. And the next thing we do then is we once again get the printer out and we get the silver ink, and then we print that, and then that will go through our big conveyor dryer at whatever temperature is needed to remove all of the solvent. And if you are fully curing it, you can also put it at higher temperatures as well to get rid of the binder, but I'm quite happy to have the binder in for this particular use. It works fine for these coasters. And then after that, you have your coaster. So these are some I've made recently just to test out cork, because cork's actually a really cool material because it's firmly stable to over 200 degrees, which means even when I put it through the oven, it doesn't come out as a smoldering lump of charcoal, which is really useful when you want to try out for floors. So this is what happens when you wire it up to a variable voltage power supply and you set your current and voltage. And when it runs through, this is what you will see on an infrared camera, which I will also be demonstrating today. And at, I think this is around 20 volts and 0.7 amps, we are getting a temperature of around 45 degrees. However, if you put it up to around 27 volts, so you increase that voltage, I've actually got it as high as 113, but I don't want to go that high today because I'll burn my hands. So the demonstration I'm about to do is with a 2 9-volt batteries, which have been put in series for 18 volts roundabout. And then we'll be able to together measure the temperature output using my infrared camera. So to show you that, I'll stop sharing the demo and show you my screen. So if I drop this down and I show you, here is the coaster, which is plugged in to a pair of 9-volt batteries, which are currently being plugged in, connected to a switch so that it's not always on. If I put my coaster back in place and I plug it in with your negative side and positive side, we can then run through it. And if I turn on my infrared camera, so what we've got today is a little FLIR one. This is a small infrared camera that can be used with a mobile phone device. If I plug it in and get it going, I do apologize, sometimes it takes a little while to warm up. There we go. So whilst that is warming up, what you do have here is the exact coaster you saw going through the process earlier. So this is our layer of carbon and this is our layer of silver. This is actually being printed around 8 times to overcome the roughness of the coaster. So that is another thing you also have to do. So if I get that around about in place, try and align it with the camera. So can I see my tiny cold fingers? Roundabout. Yes, you can see my very cold fingers, which means that we are in the right place. So if I turn this on and I try and get that in place, you can now see it's starting to heat up.
Okay, but it's ceramic.
Now, can you see that?
Mm.
Yeah, brilliant. And just to prove that this is live, there are my really cold hands. Yes, they are slightly unhumanly cold. I do have a condition.
Okay.
Cool, so I hope like that. I'll turn that off now. But as well as this one, We can also have ones which you can paint at home. So this was actually done at home using a carbon-based ink, which I bought online, and I painted this. I wouldn't recommend painting. It is a little bit tedious, I'll be honest, but you can also, if I plug that in, get it to try and heat up. Now this ink, admittedly, is nowhere near as conductive as the other one, which means that we may struggle to get it to heat up. So once again, if I try and get this and align it with my cold hands, there you go, and turn it on, you still get a little bit of heating up, even though it's not as good as the other one. But this is something you can do at home if you get yourself a coaster and you get yourself some conductive carbon ink, which in this case was just bought online. Not too much of a price.
I can't buy it
You're
online.
welcome to try and make your own. Going back to the presentation, how do we know
That's a big
that this is good enough?
no.
So go through this.
I hope. Yeah. Is it on loud?
Sorry, who is that who's talking? I can try and mute you if you're struggling, but although I thought I had muted everyone. Okay, phantom. Fair enough, we have ghosts. But what we can do is check for print consistency. So we can do this using a few things. So a good print quality is normally nice and continuous without lots of holes in it and lots of areas where it can short. So you want a good print quality, and that will give us a good electrical performance. We can check this by print roughness and also the film thickness. So when I talk about roughness, we're talking about the large roughness of the wavelengths as well as the small indentations. We can also look at film thickness. I'll tell you how we can measure that in a sec. We can also do electrical characterization. So in this case, you can use a multimeter or a source meter to check that, as well as looking at the microstructure to understand what our carbon flakes are actually doing. So let's go through that. So for roughness, we can use topographical measurements. So when I say that, I mean the form of your print. So something I use quite often is called white light interferometry. And the way that works is we have a white light source which goes through a beam splitter, will come down to your sample, and when it regroups with the other beam, will go off towards your camera. And the difference between the two will enable us to know how close or far away your sample is in all these different locations. So in this case, this is what a few printed lines look like, the very, very fine lines that I have done for other projects. And then getting that data, you can turn it into a graph, and you can actually measure how wide and how high these lines or these features are, as well as measure how rough they are, which is really useful when you're trying to understand the effects of changing different parameters on their performance. Another thing you can use is called focus variation microscopy. So this is very similar to the microscopes that can be used in schools, except this one, instead of taking a single image, will take several, and it will know the height of every image it takes. So it will take it one height, then another, then another, then another, and it will create a stack of images knowing the exact location of every one, and it will use an algorithm knowing the most in focus part of each of the pictures and comparing them to the neighboring pictures. It can figure out how high each image is. So this gives us true color roughness as well. So it allows us to look not only at the topography, but also the colors we get here, whereas this one is only using color mapping to say how low or how high something is. So these are two really cool things that we use, which you would use a lot if you were to do things like materials-based engineering, and we do use them for mechanical testing as well. And the obvious one as well is this is conductive, so we do electrical characterization. So in the case of most of the things I do, I use basic 2-point probes like you may do at school, just to measure the resistance in ohms across your sample. So I can demonstrate that. very quickly, just on screen without on the little screen. So if I were to put my multimeter into resistance mode, I could then get my probes on either side of the lines and measure the resistance across it, with higher resistance being less conductive, which is the reason why the second thing I showed you wasn't as hot. It's because it's got too high a resistance and therefore wasn't allowing enough to flow across. And another one which I particularly enjoy doing is very, very near close microscopy. So this is using scanning electron microscopy to look at things in the micro and nano region. So in this case, it uses an electron beam which is focused by a condenser lens, which then passes through a series of coils and plates, which deflect the beam in the X and Y axis so that it scans over an area of the sample surface and can allow us to see how the particles or anything conductive within it is interacting. So what I'm showing you here are 16 sets of images I took at different angles of my carbon. So what you're actually seeing here are individual flecks of graphite, which are in these exact prints. Well, one of them, this one also contains carbon black, but a few of the ones I use are pure graphite. And this is showing how all the flakes lie together, enabling electricity to flow across them in a conductive ink. So this is what would happen if you were to look really close. To give you an idea of scale, this distance here is 1 micron. So these flakes are usually between 5 and 100 microns in size, which is pretty small. So to summarize, printing is more than just producing pretty colors. You can use prints to conduct electricity, change color of light, heat, or water. It has a whole host of applications and can enable us not only to produce a variety of cool, flexible objects, but also help us develop our off-grid homes. And now you also know, if you get bored, how you can make a resistive heater just out of a bit of carbon ink, which you can buy online. So I hope you have enjoyed yourself. And I would also like to thank these guys.